When we deal with reversible reactions, we run into a scenario where we can reach an equilibrium when our forward rate becomes equal to the reverse rate. This will always happen if we've got a reaction that is reversible. Now, in a laboratory scenario, we need ways of determining whether or not our reaction has actually reached that equilibrium. Remember, we're going to get to that standstill where our concentrations no longer change, and so we need to know, have we reached that standstill yet or not? So how do we know if our reaction has reached an equilibrium yet? If it hasn't reached equilibrium yet, how do we know how our concentrations will continue to change? To do this, we use what is called the reaction quotient. We represent the reaction quotient with a Q, a capital Q. This reaction quotient gives us an indication of the reaction mixture, reactants compared to products, or products compared to reactants at any time during the reaction. So Q is going to be equal to the concentration of the products raised to some power divided by concentrations of reactants raised to some power. This should look familiar. Notice Q is set up just like K. So remember K, we did products raised to some power over reactants raised to some power. The difference here is that in calculating Q, we can use concentrations at any point in time, where K has to use equilibrium concentrations. So what is the difference between Q and K? Q is the ratio at any time in our reaction. Whereas K is specifically at equilibrium. So how do we know when to calculate Q versus K? Typically, if we don't know if we're at equilibrium yet or not, if we're not sure it's at equilibrium, we just have some concentrations that we've measured, and we're trying to figure out if it's at equilibrium, that's where we're going to calculate Q. So whenever we are not sure that you are at equilibrium yet. K is if we know we are at equilibrium. So how do we use this Q? So to determine if we've reached equilibrium yet or not, Q is compared to K. It lets us know if the reaction is at equilibrium or if it's going to continue to proceed, or sometimes we say shift in a particular direction to reach equilibrium. When we say shift, it's just referring to one particular rate being faster than another. So the rate in one direction is faster than the other direction. So with Q, we come across three scenarios. Q could be equal to K. When that's the case, we are at equilibrium, that we have reached that ratio that indicates equilibrium. If Q is less than K, that means that at that particular point in time, we have more reactants present than what we would have at equilibrium. This means that to reach equilibrium, the amount of products must increase and the reactants must decrease. So for products to increase, that means we're shifting in that forward direction. Or we say the reaction proceeds in the forward direction. So during that point in time, the rate for our forward reaction will be greater than the rate for our reverse reaction. And this will be the case until we actually achieve that equilibrium. The other scenario is if Q is greater than K. In that case, we have excess products. This means that to reach equilibrium, the amount of products must decrease and the reactants must increase. The reaction proceeds in the reverse direction until equilibrium is reached. So we want to be able to calculate Qs. We want to be able to compare them to K to determine if we're at equilibrium yet or not. And we want to determine which direction our reaction is proceeding in if we're not at equilibrium. So we can take a look at problem number 3. We're told that K is 4.18 times 10 to the negative 9th at 425 degrees Celsius for the reaction of 2 HBr producing hydrogen and bromine. Now remember that K determines the position of the equilibrium, or the extent of the reaction. Looking at K, we're asked about the position of the equilibrium. So again, we're looking to see if K is small, intermediate, or large. This K value is less than 10 to the negative third, so I have a small K. So remember again that small K means my equilibrium favors my reactants. Now, if the concentration of HBr is 0.75, the concentration of hydrogen equals the concentration of bromine, which is 2.5 times 10 to the negative fourth, we're asked to calculate Q. We're not always going to be told directly to calculate Q. Here we're just given some concentrations. We don't know what these concentrations are. They could be initial, they could be halfway through the reaction, they could be final or equilibrium concentrations. We don't know. And since we don't know, we're going to calculate Q. So to calculate Q, we've got to set up our Q expression. So it's the concentration of each product raised to their coefficients divided by the reactant raised to its coefficient. So again, we got that coefficient of 2, so we're raising it to the power of 2. Just like with calculating K, we're going to take these concentrations and we're going to plug it into our expression. So the hydrogen and bromine are both the same concentration. So 2.5 times 10 to the negative fourth times 2.5 times 10 to the negative fourth would be 2.5 times 10 to the negative fourth squared. On the bottom, my HBr is 0.75. And that concentration is squared. And this will be equal to 1.1 times 10 to the negative 7th. So if we now compare Q to K, we want to determine if this reaction is currently at equilibrium. So our Q that we just determined was 1.1 times 10 to the negative 7th. Our K, we were told, was 4.18 times 10 to the negative 9th. These two values do not equal one another. So if they're not equal, that means we are not at equilibrium yet. And since we're not at equilibrium, that means we're in a scenario where our concentrations are still changing. And so we want to know in which direction are they changing. And so we're looking to see, is Q greater than K or is Q less than K? Here, 1.1 times 10 to the negative 7th is greater than 4.18 times 10 to the negative 9th. So we said when that is the case, our reaction is going to proceed in the reverse direction. We have more products than what we should have at equilibrium. So before we reach equilibrium, we're going to find that the product concentrations go down and the reactant concentrations go up. The way we can use this in a laboratory, so for example, in this particular scenario, we paused our reaction at a particular point in time, we measured concentrations, we found that at that point in time, my reaction is going to proceed in the reverse direction. So if my goal is to create those products, their concentrations are going to go down. It would be in my benefit to go ahead and stop my reaction now and collect those products before we lose their concentrations. Now we can look at another example. Here we've told that K is 2.4 times 10 to the negative fourth. So we're asked the position of the equilibrium. Again, this is a small K. So small K means that my equilibrium, again, favors the reactants. This time we're given pressures. It doesn't change the calculation. We're going to set up our Q, and this time we're not asked for Q. we're given pressures and we're asked is the reaction at equilibrium. The way we tell that is by calculating Q. So Q is going to be, this time it's pressure, so it'll be the pressure of my products, each raised to their coefficients, divided by the pressure of my reactant, raised to its coefficient. So we plug in these pressures. So the hydrogen is 0.210, and that quantity is squared. I'm sorry, the hydrogen is 0.324. That quantity is squared. The sulfur is 0.210. And then my H2S is 0.90, and that quantity is squared. So calculating our Q, we're going to get a value of 0.0272. So again, determining if we're at equilibrium, we're comparing Q to K. So Q is 2.72 times 10 to the negative second. K was 2.4 times 10 to the negative fourth. In this scenario, Q does not equal K, so we are not at equilibrium. Again, we have a scenario where our Q is larger than our K. So again, that means that our reaction proceeds in the reverse direction. We're going to produce more reactants. We're going to lose some of our products before we reach that equilibrium. So again, Q, the reaction quotient, we write an expression just like we would with our equilibrium constant K. We set the expression up the exact same way. We calculate it the exact same way. The value we get and the difference is that those concentrations can be at any point in time in our reaction. We compare Q and K. If they're equal, we're at equilibrium. If they're not, we're not at equilibrium. So then we look to see, is it greater than or less than, and that tells us what direction we proceed in.